So let's look at portfolio risk and return. And we'll start with portfolio return. It's a simple equation. It's the return of a portfolio is equal to the weight of the first asset in the portfolio times the return of that asset plus the weight of the second asset in that portfolio times the return of that asset. It's just a weighted average of the returns of the elements of the portfolio, where the weights, of course, must sum to 1. For the portfolio risk equation, the formal writing of it's a little bit more complicated. I have a double summation where n is the number of assets and I count I equals 1 to n and then j equals 1 to n. And this notation here, sigma ij, is equal to the variance if it's 1, 1 or 2, 2, and it's equal to the covariance if it's 1, 2 or 2, 1. And very important, the covariance between 1 and 2 is equal to the covariance between 2 and 1. And so when I write this all out, I see that I get 2 of these. And so a portfolio's standard deviation, which is the square root of the variance, is equal to the weight of the first asset squared times its risk squared plus the weight of the second asset squared times its risk squared plus 2 times the weight of 1, weight of 2 times the covariance. Now we're going to adapt this slightly, and we'll also come back to this later on when we have 3 assets and 4 assets and 5 assets and n assets, and we'll do that for both of these equations. Okay, next. Let's examine the risk equation, the portfolio variance and portfolio standard deviation equation. And the first thing we're going to do is we're going to switch from covariance to correlation. And the reason we're going to do that, even though it's slightly easier to compute this with covariance, is that the correlation is far easier to understand and to interpret. Remember that the covariance, it's difficult to interpret the magnitude, and the correlation, remember, is a value between between -1 and +1, so it's much easier to interpret this value. And so we're going to start with the definition of the correlation, which is the covariance divided by the product of the standard deviation. And we're going to solve for the covariance, which is equal to the correlation times the product of the standard deviations. And then we're just going to substitute. I'm just going to substitute for the covariance in this equation, and I'm going to put in the correlation, and I end up with an extra standard deviation term here. Now, here is our new set of equations with this substitution. And I can see that I have my portfolio return equation, the weighted average of the components of the portfolio. And I have my portfolio risk equation, which is going to be the first asset weight squared times its risk squared, second asset weight squared times its risk squared, plus 2 times, well, now I have the correlation coefficient here, and then note these two terms repeat, W1 sigma 1, W2 sigma 2. And we want to start by examining the situation in which the correlation is equal to 1. And what we're saying is that the returns of the 2 assets, Asset 1 and Asset 2, are perfectly positively correlated. So what does that mean? It means that when the return of Asset 1 is far above its mean, then the return of Asset 2 is also far above its mean. And when the return of Asset 1 is far below its mean, at the same time, the return of Asset 2 is far below its mean. And in this particular case, we would say that the 2 assets are perfectly positively correlated when this relationship holds, when the amount that they vary together is equal to the amount that they vary. And what we would say economically is that these assets are not diversified, that there is no diversification. And so correlation and the correlation coefficient in this equation is a way to compute and examine the degree of diversification. And if correlation is equal to 1, then we would say there is no diversification. The assets are undiversified. So let's look at this equation and see what happens when we substitute 1 for the correlation coefficient. And so I'm just going to plug in a 1, and this is an extreme case. And so I get the weight of the first asset squared times its risk squared, weight of the second asset squared times its risk squared, and this correlation coefficient is 1, so it drops out, and so I'm just left with this. And I can recognize that this is W1 sigma 1 squared. A times B squared is equal to A squared times B squared. And I can see that this is W2 sigma 2 squared, but then I also have these terms repeating here, so W1, W2. And I notice that this is of the form A squared plus B squared plus 2AB, all of that to the 1/2. And I can see that this is actually equal to A plus B. And so for rho equal to 1, when rho equals 1, the risk of the portfolio, again, is this weighted average. It's just the weighted average of the risk of the two components. It's the weight of asset 1 times its risk, and it's the weight of asset 2 times its risk. Now, what that means is that when there is no correlation, when there is no diversification, when the correlation coefficient is equal to 1, this is the portfolio's risk. But now let's examine this third term. This is where the correlation coefficient hits. The correlation coefficient, the maximum amount this can be, is 1. It can't be any greater than 1. If it's less than 1, then it must be the case that this term is actually smaller than if it were 1. And so therefore, if rho is less than 1, if there is some diversification, remember rho equals 1 is no diversification, rho less than 1 means some diversification, then the risk is actually less than the weighted average. And so the takeaway, this fundamental result in finance, is that if rho is less than 1 and there is some diversification, then the risk will be less than the weighted average. Diversification lowers risk. Again, this is a fundamental result in finance, that diversification lowers risk. And we can see this mathematically because if this value, when it's at its highest amount, is just the weighted average, if it's lower than its highest amount, then the portfolio risk must be less than the weighted average.